Alright, and welcome to the video where we will look at using induction to prove tight bounds on some recurrence relations. In the last couple videos, we introduced some algorithms for searching sorted and unsorted lists, and we came up with these three recurrence relations expressing the runtime of them. The first and the third relation here, we came up with linear time guesses for the algorithms, big theta of n. And then for the middle algorithm, which was our binary search algorithm, we came up with the guess of log n. We used the recursion tree method to come up with these guesses. It is the goal of this video now to prove the first of these three recurrence relation proofs by giving upper and lower bounds for our recurrence. Now, in order to do this, we are going to apply the definition of big theta of n to t of n. Keeping in mind that means we need to show both an upper and lower bound. To show the big O n component, we need to show that it is less than or equal to b times n for some constant b, and for all n greater than some other constant n and not. And then alternatively for the big omega, we need to do the alternate side where we need to show it is greater than or equal to a times n, again with the same conditions. Alright, in order to prove this, we're going to use mathematical induction. I've got the proofs started here. I've just stated the recurrence relation again on the side over here in case we need to refer to it. And I've also stated the theorem here. And maybe I'll just make a little comment here, that what I'm actually trying to prove here is that t of n is in big O of n. That's what I want to prove. But what I have written here is what the definition of big O of n requires me to prove. I need to show that it is less than or equal to bn. And in fact, to be precise here, I should include for all n greater than or equal to, maybe I'll call this one n sub t for t of n. Okay, so we do want to make sure that we can pick out a b and potentially an n sub t if we need to, for which this proof will be true. All right, now we're going to carry out the proof. And usually it's helpful when we start out a proof to tell our reader what kind of proof we're going to do here. And we're going to do an inductive proof. And when you're going to do an induction proof, so we're going to say by induction, we usually want to say what variable we're doing induction on as well. We're going to do induction on n, the variable n. So now that really is inconsequential to our proof. It doesn't contribute to the proof in any way, but it does contribute in that it tells our reader what to expect. And so what they should be expecting if we're going to do an induction proof is that they should expect a base case to come up. So remember, an induction proof proceeds in two cases, the base case and the inductive case. And so here we might have the base case. And again in brackets here I might say, well, what base case am I going to select? I should pick some value for my base case here. Now, which value we pick is really up to us. We should maybe look over here at our recurrence to see what values we have. The way I've defined it here, any n less than or equal to 1 is equal to c. Which means we could pick, say, n equals 0 or n equals 1. It strikes me that maybe n equals 1 makes sense as sort of a good starting location here. So we're going to pick n equals 1. Let's see what we need to prove. Now, what we're trying to prove is that t of n is less than or equal to b times n. Well, in this case, we've just said n is going to be 1. So what we need to show, maybe I'll just put here, we need to show that t of 1 is less than or equal to b times 1. Now normally this is actually how I will start out the base case. The base case for these proofs are usually almost so simple that it seems like we're not doing anything at all. So I'm going to go ahead and do that again here. I'm going to see what we got here. I'm going to expand it a little bit more. I'm going to say t of 1. But I am going to look over here and see, look, when n equals 1, t of 1, I know what that is. That's c. Okay, so t of 1 is c, and I need to show it is less than or equal to b times 1, which is itself just b, which means if b is greater than or equal to c, then this condition holds. So usually at this step, I'll say, okay, yeah, I can make that happen as long as I pick a b that's greater than or equal to c. And remember, by the definition of theta, or big O in this case, we get to pick what b we use. So as long as it's positive. So far, this is just one condition on b. We might get some more as we go. As long as we can satisfy this condition, we're done the base case. All right, in order to proceed on to the inductive case, we need to start first with the inductive hypothesis. In the inductive hypothesis, what we're going to do is we're going to assume what we're trying to prove. Now, we need to be careful here. If we just assume exactly what we're trying to prove, we're going to be guilty of the fallacy of begging the question. If you assume what you're trying to prove, you can always prove it. And so that doesn't really get us anywhere. That's a fallacy, meaning it's not a correct logical inference. So instead, what we're going to do is we're going to make and again, we're going to assume what we're trying to prove. So we're starting here with an assumption. Assume. But instead of writing it in terms of t of n up there, because I don't want to be guilty of begging the question, I'm going to write it in terms of this other variable k that we haven't used yet. So t of k is less than or equal to b times k. I've just rewritten it and I've put k's in for n's. And again, the reason I've done that is I don't want to assume it for all the n that I'm trying to prove. I'm just going to assume it's true for all the k less than n. Okay, strictly less than, not less than or equal to. This is an instance of what we call strong induction. And it's not exactly necessary here. I'll put that as a comment again. In strong induction, we assume that what we're trying to prove holds for every previous case up to the current one n, but not including the current one n. This differs from weak induction, which is maybe an inductive principle you've looked at before, where we only assume that it holds for the last case, n minus 1. Now for our problem here, because our main case only depends on the last case, weak induction would be perfectly fine here. But in order to prepare us for some proofs coming up, where we might have the floor of n over 2 showing up in here instead, in those cases we need strong induction. I'm going to use strong induction here as well. So we've got here my inductive hypothesis. I'm just going to assume what I'm trying to prove, but again for this restricted set of values of k less than n. Now on to the inductive step. All right, in the inductive step, we have to handle the other cases that we didn't handle in the base case. Since the base case only handled n equals 1, we're now going to handle the cases for n greater than 1. Again, looking over here at our recurrence relation, we can see that that's the recursive case, n greater than 1. And we begin this step by, again, writing down what t of n is equal to. What we need to prove is that t of n, so maybe I'll write down here a little bit down. We want something like this. T of n is ... less than or equal to b of n. That's what we're trying to prove here. But where we get to start out is just with our definition of t of n in our recursive case, because remember we're in this case. So we'll write down the definition here. T of n minus 1 plus d. And again, I'll usually write a little comment here to remind my reader what I'm doing. That's from the definition, and since I have it here, maybe I'll draw a little arrow. That's what I mean by the definition. Now the next step I'm going to do here is very important. I want to use now the inductive hypothesis to replace out this t of n minus 1 term. And to do that, we're going to do a step of double substitution. The first thing we're going to do is we're going to take this n minus 1 term and sub it in for our k term here. So let's see what we get when we do that. We'll get t of n minus 1 is less than or equal to b times n minus 1. Interestingly, this would be exactly the inductive hypothesis we would have gotten if we had just done weak induction to start out instead. Now we're going to use that notice we have this t of n minus 1 term here, so we can use that to replace it, get rid of it. So I'm going to say less than or equal to here, replacing out this term with what we have on the right-hand side here, b of n minus 1, b times n minus 1, I should say. Don't forget the d, it comes down. And again, if we want our reader to know what we're doing here, I might say that's by the inductive hypothesis, okay, above, or we substitute it in here. Now I call this double substitution because we do two steps. First, we take this term here, n minus 1, and we sub it in for our k. That gives us this hypothesis here. And then we're going to take this term, or rather we're going to substitute n for this term here using the right-hand side, the b of b times n minus 1. And that got us to this step here. Now, we still want to get down here below. We can see we're kind of getting close there. But we need to do a little bit of algebra to finish this off. So I'm going to multiply my b through here. We're going to get bn minus a b plus a d. And now we've actually got that term we want. You know, we've got the bn. We just have these sort of extra hangers on. And maybe we can get rid of them. Let's just start by doing some wishful thinking. If b was exactly equal to d, they would cancel out and we'd get equality here. That's exactly what we want. Well, we actually have a little more wiggle room than that. We're allowed to do less than or equal to. So as long as whatever this cancels out to makes the whole thing less, meaning is negative. So again, if this whole thing, when we cancel out the negative part, is greater than the positive part, then this last step will be true. So I might say here, as long as b is greater than or equal to d, this last step works. Now I need to gather together my conditions. I got one here, I got one here. I need a b that's bigger than or equal to c and d, and luckily there's an easy way to do that. We can say let b be equal to the maximum of the two. Okay, that way we're guaranteed it's bigger than both of them. I've noticed in the past some students have asked me, well, what about c plus d? C plus d works too, but this is just the minimum such b that's going to work. So we'll pick this b here. And what values of n did it work for? Well, we started at 1, so we can conclude, by induction, what did we show? We showed that t of n is less than or equal to b times n for all the n greater than or equal to 1. And we're done. The little box here meaning QED, meaning we are done. I believe that's Greek for what has been, or for what was to be proven. Okay, so I'm basically saying what was to be shown, we have now shown it, we are done. And that just sort of shows you a little bit about a proof, in case this is the first mathematical proof you've looked at in a while. Often in a proof, especially a more complicated one like this using induction, there are kind of 3 stages. I say proof, I'm going to say what I'm going to do, how I'm going to prove it. I'm going to prove it by induction on n. Then I do it. Here I prove it by induction on n. And then I finish off here by saying what I did. Look, by induction, I proved this. So now I'm done. That's usually just a message to your reader saying, look, we got where we planned to go. Okay, and so hopefully if you followed along with me in this proof so far, you got where we were trying to go here, and you're confident that we've just proven for this recurrence relation that we're in big O of n. All right, to conclude our proof, we need to show the big omega side of the bound as well, which now is going to be a lower bound, which now you can see I've switched around to our other definition, where now my less than or equal turned into a greater than or equal, and I just relabeled my b and a to keep them separate in my mind. And again, we might choose a different nf here. Well, we showed it was true for all n greater than or equal to 1 in our last case. We might be able to do that as well in this case. So again, let's try to build our inductive proof. We can do that with starting with our base case. Again, here, why not start where we started last time with a simple n equals 1. And let's go straight for it. We're going to say, well, what do we have here? T of 1. What is our T of 1? Same as before, it's still C. And now what do we need to show? We need to show it's greater than or equal to A times 1. Well, that again is just A. Well, let's just check here. As long as A is less than or equal to C, then we're good. Now, on the other side, we had, on our last proof, we had B was greater than or equal to C. Now we have A is less than or equal to C. In the case where we had B is greater than or equal to, we actually have a little bit of freedom, a few extra degrees of freedom in choosing our B, because remember, the only restriction we had prior on B or A is that these are positive constants. They must be, greater than or equal to 0. So A must be greater than or equal to 0. Well, now we've got a little bit of squeeze zone here. Our A must be between C and 0. There's a little wiggle room there. Hopefully we're still good because we know C is positive. Okay, but when we had it before, when B was on this side, the only thing pinching it on the left is infinity, basically nothing. B could grow as large as it wants. A can only grow as small as 0, and we want to be sensitive of that when we go. But here it looks like we're okay. We get to pick an A as long as we pick one less than or equal to C, and we know C is positive. Okay, so let's head on to our inductive hypothesis now. All right, just like our last example, we're going to have our inductive hypothesis stated in terms of K instead of N. But we're going to restate what we're trying to prove. T of K is greater than or equal to A times K. But again, for restricted values of K, the K that are less than N, strictly less than N. And now we can proceed to the inductive step. Again, we're going to, in this step, do the cases remaining where N is greater than 1, which means we're going to begin with our definition of T of N, which again above, copying from our recurrence above there, we're going to get T of N minus 1 plus D. Again, maybe a little note for ourselves. This is by the definition of T of N. Okay, the next step, we're going to be conducting an approximation using our inductive hypothesis. We want to again do our double substitution. We're going to take our N minus 1 and plug it in for K. And if you need to, on some scratch, go ahead on the side and write down what this means. That means T of N minus 1 must be greater than or equal to A times N minus 1. Okay. But that means we can now replace out this term here. The T of N minus 1 term must be greater than or equal to A times N minus 1 plus our D. And again here, we're going to get AN minus A plus D. And we're trying to show that this is greater than or equal to A times N. And we see the exact same pattern that we saw before. We have a negative component and a positive component. We want them to cancel out. It would be nice if they're exactly equal, but we have more wiggle room than that. We want this whole term to be greater than or equal to this one, meaning we want the positive component, the D, to cancel out to be greater than or equal to the A component, the negative component. So again, we've got ourselves a condition here. Okay, adding that to our condition above, we need A to be less than or equal to C. Here I've got it backwards, but A needs to be less than or equal to D. So putting that together, let's check. Let our D here be equal to the minimum of C and D. That way our A, oops, I said our D here. Let's say our A is equal to the minimum of C or D. That way it satisfies both our conditions here. And then we can say, so by induction, what have we shown? We've shown that T of N is greater than or equal to A times N. Remember, we just selected A for all of the N greater than or equal to, technically, 1. That was the one that we selected here. 1 was the first value that we proved. We proved all the ones greater than N or greater than 1 here. So once again, we are done. Okay, so hopefully in this video we've had a quick review of the inductive proof technique using recurrence relations. It also gave us a quick introduction to strong induction instead of weak induction, something that was not technically necessary in these two proofs, but will be necessary in the next collection of proofs that we will do. I am going to put off those proofs to the next video, so please stay tuned for that. Thanks for watching, and we'll see you in the next video.